Partitions are waiting for the last possible minute to scurry across through the heat to get here.
Yeah, we've probably got stuff to do.
Not too much, should be writing pieces.
You have to use this, otherwise Michael is going to complain.
Am I being recorded or is this just you? Plenty of parking. There might be cheaper parking somewhere, but
It's just a question. Since 2020, and it's hard to find parking spaces. Because anytime after this is an issue of that, there are a few. But if you come to this time of day to jump up them.
I just move the street parking on the
Yeah, well, it's a point, so you've got this wonderful sophisticated motorised system. Whereas in the good old days, you could just...
I mean, I'm pretty sure that if you hang someone on it, the motor will give up.
But yeah.
Yeah.
I don't particularly into the IT system.
Did you come in just for the seminar?
You going to the hot side and research?
Wouldn't mind a beer? You?
I will want to be straight after this. I've got a meeting, another board meeting, so the data issues.
For an hour. Let's see whether I still want to be.
Probably more likely that you'd do something very special to do with
Just check. No, just about whether I go with him, you know.
not one of these, make sure I know it.
Thomas, microphone. Oh, you got it. Just remember.
So I'm not.
Thank you.
Yeah, actually, so Dad, did you read the abstract for this talk? Because apparently Jason's talking about your work.
Am I?
Yeah,
You didn't read your own abstract.
the seminar you got a copy and pasted the wrong names for the...
No, I didn't change one name at one point.
Is that the email version?
Yeah, and also on
I was
Slack.
reading the Slack version,
On
which
Slack
is
is-
correct. The one you put on Slack was right.
Maybe I didn't copy everything
In
over.
the preamble, not in the actual... There's the two-sentence preamble where he's trying to be being collegial and friendly.
Anyway, welcome to the Complex System Seminar. Jason, this is the audience. Audience, this is Jason. It's very simple. The further back they say it, the more nasty they are. With respect to Jason, yeah, I'm sitting back there. It is clear he's a clever guy. He got me in Stats 3061. He got David in Math Network Science. He got Shannon in Complex Systems. And then he decided he works with Michael. He's clever. Just you saw how useless the rest of us are, so obviously. Anyway, today you are going to talk about your MZ vocation scholarship work
Yeah.
on assessing partitions of dynamical systems.
Perfect. Do I need to wear this? Can I just hold it?
Yes, you can hold it, you can wear
Alright.
it, you can... It's anyway only Shannon who is going to listen to it afterwards, so...
Okay. Perfect. All right. Yeah. So yeah, if we haven't met, my name's Jason. I've just finished my first 3 years of undergrad maths, and I'm doing my honours in applied maths this year in 2024. And over the summer, as this template suggests, I was awarded a summer research scholarship under the AMSI program, and so I've been working on this project, assessing partitions of dynamical systems, under Michael's supervision. As part of this scholarship program, I'm attending a conference that AMSI is running next week. And I'd much rather be stumped by a question here than next week. So any hard questions you have, please fire away. Cool. Okay, so structure this talk, we'll start out with a bit of background motivation. I can skip some of this because you guys all know a bit about complex systems. We'll go into a bit of methodology, discuss results from test systems, and then finish with some conclusions and look at what next steps are. Okay, I can skip these. Partitioning, okay, so we're interested in partitioning dynamical systems, so essentially we start off with a system like, say, the Lorentz system, which exists in this case, R3, 3D space. What we're interested in doing when we're partitioning is splitting up into these discrete sets. We discretize the points in time. Each point is assigned to a set, and each of those sets is associated with a symbol. And so we move from this 3D space where each point is described by a 3D vector into this symbol space where each point is just described by the symbol that it's associated with. This is a useful thing to do because it allows us to apply all sorts of symbolic dynamic techniques to analyze the system, and is used in some applications, for example, in reducing noise in certain circumstances. So there are obviously a lot of ways we can go about partitioning a system, and we have good and bad partitions. So because we're using the partition to represent the system in another way, the ultimate goal of the partition is to try and preserve the important underlying system dynamics. Another way of thinking about this is that the resulting symbol sequence that we get of the series of points after we apply the partition should retain information that exists in the original system. So as a simple example, with the Lorentz system, we're interested in retaining this chaotic behaviour when we switch from the left to right wings, for example. So this partition on the left is what we'd consider probably a better partition, because this chaotic behaviour when we switch between the two wings is captured when we switch between the symbols 0 and 1. If we look on the right hand side, for example, we've got an example of a bad partition because that switching still exists in the system, but when that switching does occur, it's all occurring in the red region. It's all assigned symbol 1, and so you lose that information in the resulting symbol sequence of that partition. So the motivation for this project, we see that ordinal partitioning recently is generally what's been used to partition dynamical systems, and the reason for that is that it's been shown to be useful and effective in a lot of different situations. Aside from ordinal partitioning, though, there are other methods. There has been some existing work on estimating generating partitions on two-dimensional maps. So these generating partitions offer another example of a potential high information partition that we can find. But a lot of this work has not been extended to continuous systems or to high dimensional systems. So a lot of it just exists on the 2D maps. So what we're interested in doing is finding alternative partitioning methods to the ordinal partition and seeing if they can offer higher information superior partitions. Part of the problem we run into here, though, is that there's currently no rigorous method for assessing how good a partition is, which makes it difficult for us to take two partitioning methods, compare them, see which one is higher information or better. So what we're interested in doing in this research is two things. First of all, to develop some kind of metric that allows us to assess how good a partition is. And secondly, once we have this metric, to apply it to a series of different partitioning methods and see which is the best performing under our metric. So given this is quite an exploratory kind of process, we follow kind of like a scientific sort of method, if you will. So we start off obviously developing this metric to assess partitions. We then identify a series of test cases. So this includes a spectrum of different systems and partitions, which provide a broad cross-section of what we might encounter. We select these, knowing that we expect these systems and partitions to behave in a certain way. And what we then do is verify the performance of a metric on these systems. So if we're testing what we know is a good partition, we can test our metric on it and check that our metric does indeed say that it's a good partition, likewise for a bad partition. Once we verified this and we're certain that our partition measures and does what we want it to do, we can then apply it to some new systems and use that to draw conclusions, for example, finding better partitioning methods. Okay, so I will explain first how this mutual information-based metric that we've come up with works. So the idea here is essentially, if we imagine that the situation here is we're partitioning, if we're making observations from a dynamical system with low precision. So that's these large black circles here. That's what they represent. So we've got 3 observations here, for example. We have the shadowing lemma, which tells us that given a set of these observations, we're able to find at least a set of at least one trajectory that passes through these 3 points. If we then zoom in on, say, the rightmost point, what we see is that because we not only know that the point passes within this observation's region of error, but also that it has to satisfy one of the trajectories, we've effectively reduced the area where the real point that we observed could exist to what is equivalent to making one high precision observation represented by this red circle here. So the underlying idea here is that a sequence of low precision points should provide us the same information as taking one high precision measurement. So this is a property that's going to be preserved in dynamical systems, and given that we want our partitioning scheme to retain the information that exists in a dynamical system, we should therefore also make sure that the symbol sequence resulting from a partition also retains this property. So what does this look like in a discretized symbol sequence? So if we consider a fine partition, that is a partition which has small sized partitions with with the state space being split into lots of different partitions, that's equivalent to looking at a point with high precision. Likewise, if we look at a coarse partition with large partitions, that's equivalent to looking at a point with low precision. The other thing we can consider is the partition history of a point. So we're interested in looking at coarse partition history, representing like a series of low precision observations. The idea here is that we look at a point, we look at, say, 5 points that have been visited on that same trajectory previously to visiting this point, and we can look at the symbols assigned under a coarse partitioning regime to those points. So the way that we try and retain this property of low precision points containing the same information as a high precision point is that looking at a point's fine partition assignment should provide the same information as what we get by looking at its coarse partition history. And the way we can quantify this, how much one thing tells you about another, is by looking at mutual information. So in this case, looking at how much random variable x tells us about random variable y, or vice versa, random variable x is going to be the distribution of fine partition symbol assignments within a dynamical system, and random variable y is going to be assigned to the distribution of coarse partition histories. So to illustrate this a bit more clearly, we have a dynamical system here in the left 2 figures. So on the left we have a coarse partition. It's been split into 2 partitions. In the middle we have a fine partition, so we've got 20 partitions here. What we're interested in knowing is looking at a single point and finding out how much its fine partition symbol assignment tells us about the coarse partition assignments of previous points that have been visited on that same trajectory. We can then calculate that across all the points, and that gives us the mutual information between the 2 variables. Knowing this, we then repeat this for various values of k being the number of partitions in the fine partition, and we end up producing a graph that looks something like this on the right, with mutual information versus k. And we'll see a lot of these figures in this presentation. So this solid blue line through the middle is an average of 10, and the shaded region around is standard deviation across 10 trials. Okay, so we've described how this metric works. We're looking at the test systems now. So these are the different dynamical systems on which we test various partitioning methods. So we look at the Henon and Ikeda 2D maps, Lorentz-Loessler 3D flows, We look at the Duffing oscillator, which doesn't actually display, with the parameter set we've selected, doesn't display chaotic behaviour, but is simply a periodic orbit. And we add varying degrees of noise to this to see how our metric reacts to increasing or decreasing noise in the system. We also test a couple of hyperchaotic systems, the Mackey-Glass delayed differential equations. And below are a couple of transformations or processes we can apply to our system. So those are time delay embedding, and we can generate random data using surrogate data. So I'll explain these two processes briefly below. So the idea behind time delay embedding is we take this one-dimensional system and taking a series of points with a certain delay, we convert it into a 3D series. So for example, in the one-dimensional series, the points 492 become the 3D point with coordinates 492 in 3D space. What this looks like essentially is down in the bottom left, we have the Lorentz system. We take an observation of only one dimension, which is the x-coordinate, and then when we reconstruct it using this time delay embedding process, we get a topologically equivalent attractor. So there are a couple of reasons why we might want to do this. First of all, when we're dealing with real data, oftentimes we don't have access to the entire system, and so it might only be practical for us to observe one dimension of the system, and we can then use this process to reconstruct the dynamics in the original 3 dimensions. The other reason this is useful, specifically from a partitioning and using our mutual information perspective, is that when we apply time delay embedding, each point now contains information about, in this case, 2 previous points that the trajectory is visited. And if you recall, our mutual information metric is interested in the mutual information between a fine partition assignment and the previous points that a trajectory has visited. So using time delay embedding can allow us to possibly increase the mutual information of a partition. So that will become relevant a bit later. The other process here is surrogate data. So yeah, we use this surrogate data to generate essentially random systems by removing any temporal correlation from the data. So we do this, there are a lot of ways we can do this which are more sophisticated, but we just do a pretty simple method of drawing with replacement from the original data to produce a random orbit. Okay, so these are the test partitions we test. We have 4 here. 2 good ones, 2 bad ones. Again, the idea being that we want to make sure that our metric can tell the good partitions are good and that the bad partitions are bad so that we can trust it. K-means is a machine learning clustering technique which essentially aims to split a data set into clusters where you minimize the distance between the points in those clusters and the mean of each cluster. Ordinal partition, I'll go into a bit of detail in the next slide. And the 2 bad partitions that we test, first of all, is slice partition, which is just taking one axis of the system and splitting it up into equally sized bins along that axis. And the random partition, as the name suggests, we just randomly assign each point to one of k different symbols. Okay, so the ordinal partition here, we apply a similar process to time delay embedding. So if we take these coordinates 492, for example, what we will then do is taking those 3 points, assign them a rank order based on the magnitude of the coordinates of the point. So for example, 492, 4 is the second largest, 9 is the largest, 2 is the smallest, so this gets assigned sequence 231. Likewise, 738 is 213, and so on. And then to map these to a single symbol, we then give them a symbol based on how large that concatenated number is of all the 3-digit numbers you could produce. So for example, using the 3 numbers 123, 231 is the 4th smallest number you can produce, so we just give that symbol 4, so on. Another way to think about the ordinal partition is geometrically. So we take the Lorentz system, we apply our time delay embedding to get this embedded attractor, and then what this looks like geometrically is we're splitting it up using 3 hyperplanes, x equals y, x equals z, and y equals z, and assigning each of those 6 wedges that are produced to a symbol. The intuition behind this is that what we're doing with the ordinal partition is comparing the magnitudes of subsequent points, say xt, xt plus tau. And when we're in embedded space, xt, xt plus tau are the axes of our space, and so those lines x equals y, x equals z are going to be the critical lines over which they're split. So yeah, in embedded space, it looks like these wedges which are split along those hyperplanes, and it looks a bit stranger when you take it back into the original state space, but same partition. These next couple of slides are just a few images to give a couple of examples of what these systems and partitions look like. So K-means gives you these clusters, these kind of blob shapes that are split evenly around the attractor. The ordinal partition we discussed above. On the left here is the Duffing oscillator. So we've applied the slice partition here, so you have those stripes along the x-axis. And the reason it looks kind of fuzzy is because we have applied Gaussian noise to this attractor. And then on the right we have the hyperchaotic map. Again, it's a bit cut off on the edge here, but it's, again, looks like a bit of a mess because we've applied a random partition here. Okay, so we're going to look at verifying this metric now. So we're going to test it on these test systems and partitions that I've outlined, and we're going to check whether or not it gives us the expected behaviour. So we're going to look at a series of these mutual information versus K graphs, and there are two things that we're interested in looking at. First, we're interested in looking at the actual value of mutual information shown on the y-axis. And the second thing we're interested in looking at is whether or not mutual information increases as K increases. With a good partition shown on the left, we expect that you're going to have a high value of mutual information, and also that as your partitions get more and more fine, as your K increases, you're going to get more and more information about the history. This is kind of analogous to thinking back to our dynamical system. You take more and more observations, you gain more and more information about the possible trajectories that could be passing through those points. And yeah, on the other hand, we have a bad partition here with low mutual information values and a less clear upwards trajectory. Okay, so the first case we'll look at is a random partition. Now the random partition is bad. We expect low mutual information, no significant growth. And this is what we observed tested on 3 different systems here. So no surprises there, tick for the metric, does what we expect. This next set of data we're going to look at is surrogate data. And so we've got 2 examples here, which is a surrogate produced from the Ikeda map and a surrogate from the Lorenz system. But all the surrogates are quite similar. And so again, the surrogate data being essentially random data, we're expecting what is probably, it's probably not going to be, you're not going to be able to partition effectively on this as there's no temporal correlation. So the K-means does what we expect. We see that it's low mutual information, no significant growth. The interesting thing we observe though is that the ordinal partition actually does okay on this surrogate data. And so the reason this is the case is that when we apply the time delay embedding to this surrogate data, each point now contains some information about the previous points that the trajectory is visited. And so through this process of applying the time delay embedding, we kind of generate some temporal correlation in the data. And this is what allows the ordinal partition to be a bit useful. Because each point now has information about the previous points, when we partition in the transform space, that gives us some information about previous points that the system has visited. So this is kind of due to the process of time delay embedding rather than the ordinal partition itself. So if we were to apply time delay embedding to the system and then perform a k-means partition, we also observe that we end up getting some information about, we end up getting some mutual information between the fine partition assignment and the trajectory history. Another system we look at here is the Lorenz system. So as we expect, we try the slice, k-means ordinal partitions. As we expect, the slice partition does worse than the other 2 systems here. There's a lower value of mutual information, and as well, there's less of an upwards trend as k increases. K-means perform slightly better and ordinal slightly better than there. So nothing too surprising here. One interesting observation we make here is that on the slice partition and the k-means partition, these green lines, which represent slicing along the z-axis and embedding in the z dimension respectively, give us much higher mutual information than the other embedding dimensions. The reason this is the case is that if we look at the Lorenz system, again, the interesting chaotic dynamics occur in the switching between the two wings. But those two wings are essentially indistinguishable if we're looking along the z-axis. So what happens when we slice along the z-axis or apply embedding along the z-axis is that the orbit becomes a lot simpler. We lose the complexity of switching between the two wings. And this is pretty evident if we look at an image of what the z-embedded orbit looks like. It's gone from these kind of two interacting wings into just essentially one roughly circular orbit. So that simplification of the system means that it's much easier to predict. Sorry, there are much fewer possible locations where the orbit could have gone, so it's easier to predict what the history was, and therefore you get high mutual information between a partition assignment and the history. The other interesting point then is to look at why Z embedding is not much more effective than the other embedding dimensions on the ordinal partition. So if we look at what the coarse partitions look like for the ordinal partition, for course we've used k equals 2 for all of these, we can see that for the x and y embedding dimensions, the coarse partitions are continuous. Whereas for the z embedding, the coarse partition is non-continuous, meaning that there are two locations where you can switch from symbol 0 to symbol 1 and symbol 1 to symbol 0 equivalently. This means that it's much more difficult to assign a given history to a certain fine partition assignment because there are two locations where you can switch from one symbol to another. And this discontinuity ends up reducing the mutual information, which kind of provides us with a heuristic explanation as to why the ordinal partition in Z embedding, despite being Z embedded, is not outperforming the other ones as we'd expect. So again, the system here, some behaviour that we need to go into a bit of depth to explain, but everything's kind of as we would expect, and it's all explainable and predictable. The one thing that we do need to kind of be careful of here is that this suggests to us that just because mutual information is higher, it doesn't necessarily suggest that the partitioning method is better. It could be the case that when you apply, the certain embedding as we've seen here, the orbit somehow changes. So it's a bit more difficult than naively looking at mutual information and using that to assess which partitioning method is going to be best. The last case that we look at here, which I'll describe, is the Duffing oscillator. So again, slice performs worse than k-means, worse than ordinal. And what we're testing here is increasing the amount of Gaussian noise that we're adding to the system. And again, as we expect, as we increase the amount of noise, the mutual information goes down as the system becomes harder to predict and associate a current point with its history. So again, metric does what we expect here. We did look at a few more cases which I won't go through, but our conclusion here essentially is that the metric works, behaves as expected, can tell a good partition from a bad partition, and therefore we can trust it when we go forward to explore and assess other partitioning methods. So, our next part is then to find these good partitioning methods. So, there are three cases that we look at here. The first is comparing k-means partitioning to ordinal partitioning and seeing which one's superior. The second is partitioning based on coarse partition history, and the third is looking at a weighted ordinal partition. So first, k-means versus ordinal. So we have already looked at k-means versus ordinal previously when we were trying to verify that the metric works. But what we were doing was giving a somewhat unfair advantage to the ordinal partition. The reason that is that with k-means you can choose whatever k you want and partition a given system into as many partitions as you want. With ordinal, however, the number of partitions that you produce is restricted by how many points previously you look at, essentially what time delay, what embedding you choose. And so what happens is that to increase k for the ordinal partition, we have to increase the time delay embedding. So we let the ordinal partition look further back in history and give it more information, giving it an unfair advantage. So we rectify that here by increasing the time delay embedding dimension for k-means as well as we increase k. But as this graph shows, we still end up seeing that the ordinal partition ends up outperforming the k-means partition. We see similar behaviour for the Rossler system. We test this in a few other systems as well, but essentially the conclusion here is that the ordinal partition is probably superior to the k-means partition. The next method we look at here is partitioning based on coarse partition history. So what we're doing here is kind of taking advantage of the metric a bit. So this metric measures the mutual information between fine partition, coarse partition history. So what we're thinking here is, why not maximize the mutual information by assigning fine partitions based on coarse partition history, making them contain the same information? The way we do this is we apply a coarse partition first, P2, take a point x, look at its history, and if x has history symbol sequences, for example, 0, 1, 1, 0, 1, we just interpret that as a binary number and assign it the symbol 13 in the fine partition. So we have 4 lines here on this graph. The orange line at the bottom is your regular k-means partition on the Lorentz system. The green line is using this kind of hacking method where your original P2 partition is using k-means partitioning. Your blue line is a regular ordinal partition, x embedded, and your red line is using this hacking method where your initial partition, P2, is done using the ordinal partition as well. So, unsurprisingly, given that we've kind of designed this method to maximize mutual information, we see that it does better than our other methods. The other thing that we see, which aligns with expectations, is that at k equals 32 or 2 to the 5, we see that mutual information ends up plateauing for these hacky methods. The reason that is that when we're measuring mutual information, we're only looking, this is kind of a parameter choice, we only decide to look at 5 previous points to measure mutual information. And so when you're looking at those 5 previous points to assign your fine partition, at that point you've got a one-to-one correspondence between your fine partitions and the coarse partition histories, and so you maximize mutual information there. If you decide to look further back in history, all you're doing is splitting those 32 partitions in half again, and that's not providing you any extra information. So yeah, we see that the hacking method that we've come up with does outperform the ordinal partition on this set of data. We have reasons to be skeptical about this though, because any metric is not going to be perfect. It's not measuring exactly what you want it to do. That's what a metric is. And if there's any issue in the metric, then because this method's kind of exploiting it, then it's going to be subject to that. And so essentially the issue we're running into here is optimizing for the test for how good a partition is rather than actually designing a good partition. So we have some thoughts on how we can genuinely test this partitioning based on coarse partition history to see if it actually is good in practice. But yeah, I'll talk about that at the end. This last additional partitioning method that we look at is a weighted ordinal partition. So the idea here is that in 3D space geometrically, these ordinal partitions look like the hyperplanes x equals y, x equals z, y equals z. So we form these 6 wedges. The question here is, where this originated was geometrically, what if we were to change the gradients of these hyperplanes? We also considered changing where they intersect. Currently these intersect at the origin. But if we consider looking at, say, one dimension of a chaotic orbit, if it eventually ends up roughly where it starts, it increases, decreases, and so you're likely to get points which are kind of like surrounding that 0, 0, 0 origin space. And so it makes sense for us to leave these points intersecting at the origin, that's where the wedges all intersect, but we're interested in looking at how we can change the gradients of these. An equivalent problem here is to just consider the point x with this history and look at weighting the history using these parameters a1, a2. And that does the same thing as changing the gradients of the hyperplanes, but it's just a bit of an easier way to do that. So what we're interested in doing is sweeping across different a1, a2 values and seeing how that affects the mutual information we get. So this is our Lorenz ordinal X-embedded system. On the y-axis of this graph here, we have A1 values, on the x-axis A2 values. And lighter means higher mutual information, darker is lower mutual information. So kind of two interesting areas to look at here. You have this kind of curve going along the side here in this dark area, and then you have this light area in the top left corner. So the highest mutual information in that curve on the side is the point 1, 1. So that's our regular unweighted ordinal partition. Gives us a mutual information of 1.27. So, as we expect, it's good that the ordinal partition does decently well here. The other interesting area, though, is obviously that top left light region. So we pick a point there where we have A1 equals 2, A2 equals 0.5, which gives us a mutual information of 1.4. So slightly higher than what we got with the ordinal partition. So it'll be interesting to look at what's going on here. On the left, we have our regular unweighted ordinal partition, and on the right is the weighted partition with high mutual information. So heuristically, looking at these visually, what you see is that the ordinal partition on the right has slightly nicer looking like chunks. Basically, the partitions are clumped together a bit better, they're larger and they're less spread out. If we look at what this looks like in embedded space, it becomes a bit more clear what's happening. So you can see that in both these cases, they appear to have been split by these hyperplanes. On the system on the left, it appears to be not filling out the space completely, and so the vast majority of points are in those blue and red wedges. When we change the gradients of those planes, though, those wedges end up filling up the space of the attractor a bit more evenly, and that's most likely what's lending it the higher mutual information. So what optimizing for the ordinal partitioning weight seems to do is help us counteract the problem of this attractor not filling out the space. An equivalent problem, though, or like another way we can kind of unfurl this attractor a bit, is to simply increase the embedding delay. So before we were using an embedding delay of 10 points. This is what that same attractor looks like when we use an embedding delay of 20 points. The resulting effect is that it is spread out in the 3D space a bit more. It's spread more evenly between the wedges. And as a result, with your unweighted ordinal partition, you end up getting a similar mutual information value of 1.42. And this is made a bit more clear if we apply the same analysis we did before to the system with the longer time delay embedding. What we see is that you get this similar kind of curve shape, but the point at 1, 1 is the one which maximizes mutual information. So what this kind of suggests is that we've fixed the same problem of spreading out in state space by increasing the time delay embedding and made it so that we don't need to adjust the gradients of our hyperplanes to make sure that the attractor is spread evenly between these wedges. So it's interesting that we can use the weighted ordinal partition to maximize mutual information, but whether or not this is useful or practical remains to be seen, because from these results it seems like maybe we can just achieve the same effect by choosing a more appropriate time delay embedding. Okay, so those were the 3 methods that we tested, and those are the results that we ended up getting. So a few further questions we want to investigate. First of all, does this hacky assigning fine partitions based on coarse partition history method, does that offer any practical improvements over the ordinal partition? The way we are thinking about going about doing this is to test how well they can track the largest Lyapunov exponent on a logistic map. And so this will give us an example outside of the metric itself of seeing whether or not this method is effective at detecting regime changes and detecting chaos in a real world dynamical, not a real world, but a practical dynamical system. The other question we're looking at is whether or not there is a use case for optimizing the weighted ordinal partition, or whether it is just doing the same thing as increasing your time delay embedding. And lastly, now that we have this metric, can we find other partitioning methods, test them, and see if they're superior to our existing ordinal method? Cool. That's everything I've got here. Thanks.
Thank you, Jason. I've been asked by someone who's sitting almost as far back as me that if you get questions, you please repeat the question so that he might understand them this time. Any questions from the audience, please?
Yeah.
Okay. Other than the hacking method, so it's a little unclear as to how you're picking the fine partitions. And presumably if you want, to be doing a like-for-like comparison, you want to be using the same method of picking the fine partition for all the different coarse partitions that you're testing, right? Or is that not right?
So what we were doing here was, so I'm not sure I fully understand the question. I'll explain this again. So what we were doing was we were...
So I'm not really interested in the hacking method.
Yeah.
But presumably you're using something other than the hacking method in the other cases.
So
I was
the
unclear
question
as
is
to
about
what
where
that
these
was.
fine partitions come from.
Yeah, where's the
for
fine
the
partition
earlier,
come from?
for the earlier
This is
methods.
like a proposal for a fine partition, which I'm skeptical of. How were you doing it before?
So the other methods we apply to the fine partition, typically we use the ordinal partition. So that's what we were kind of benchmarking the rest of these methods against.
When we talk about fine, the parameter to determine fineness for the other partition was k, the k means. You choose whatever number.
So in every case we were using the k-means method to choose the fine partition.
Well, for that method, so there's four methods, right? Sorry, Jason.
Yeah, no.
There's four methods. One was the k-means, where you can choose different k's to make a finer or coarser. The ordinal one, where you're looking at the rank order of your successive data points. If you take a longer history, you get a finer partition, except you don't have freedom to choose any number of symbols because it depends on
So you're saying that in some sense the method that we're testing gets to choose its own fine partition?
Well, we've got a series of methods that generate coarser or finer partitions depending on the parameter of that method. What we're looking at is how well they perform.
Okay. I don't understand why you wouldn't want to do a like-for-like comparison. You use the same fine partition for different coarse partition methods.
Okay, I see. So we didn't actually test that. The reason for doing the coarse partition and the fine partition in the same method is that our initial kind of first principles thought for this system is that if we consider both a coarse partition and a fine partition, the fine partition should provide us information about the coarse partition history. And that is the case for a given partitioning method. So if we apply all of these partitioning methods, we can apply to produce both the coarse and a fine partition. And so by doing both in the same method and seeing how much information is shared between the two, that should tell us, our thought is, how good the partitioning method is. So that's why we do the coarse and fine on...
I just worry that the partitioning method itself might be kind of blind to some aspect of the system which will be picked up by a different fine partitioning method. So if you change the fine partitioning method, you might suddenly find maybe your system looks a lot worse in terms, or rather it would be that something else looks a lot better, I guess. Okay. My intuition would be to do a like-for-like comparison between coarse partitioning methods by having a standardized method of producing a fine partition. Okay.
Sarah? You have to speak up, even though I can't understand you.
Can you please explain it again? How did you make your ordinal partitioning weighted?
Oh, sure. So the question was how we made the ordinal partitioning grader. I don't need to jump to the slide.
Weighted.
So the weighted ordinal partitioning.
Yeah, explain.
Oh, yeah, sure. So we fix the weighted ordinal partition with a time delay dimension of 3. So we're looking at 3 previous points.
Is that that be t minus tau?
Yes, good point. Sorry, that is meant to be t. Yeah, that's meant to be t minus tau. So we've got t minus 2 tau, t minus tau, and t. Thanks, I'll fix that. We give xt minus 2 tau and xt minus tau coefficients a1 and a2. And then we're sticking those into our kind of like rank order sort algorithm and using those to determine what symbol we give. So if you had, for example, 3 previous points, 1, 2, 3, that would have the ordinal sequence 1, 2, 3. But if we said now A1 has value 4 and A2 has value 1, your ordinal sequence now becomes 4, 2, 3. And so your ordinal sequence becomes 3, 1, 2.
I was thinking that because on the picture for the Lorentz attractor,
Yes.
you were comparing the, exactly
Yeah.
these two. But it means that by choosing, just by looking at any weights, looking at different weights, we can put the sections on any part of the attractor that we want, and just changing these sections of the whole attractor just by choosing different weights on it.
So could you explain your question again, please?
If just imagine in 3D that if
Yeah.
I'm changing A1 and A2
Yeah.
and choosing the different, I can put these boundaries of each ordinal partition on different part of the attractor, and I can actually put a section on the location that I want.
Yeah, essentially. So what's happening geometrically when you change the values of A1 and A2 is you're changing the gradients of those partitions, and as a result, different parts of the attractor are moving in and out of different wedges.
And they probably create one more region, or just getting rid of one of the region. I mean, by just looking at m equal to 3, that's probably not easy to get rid of a region. But if I'm using the ordinal partition with higher dimension, that probably cause to getting more region or less region,
Okay.
and can control it in a way that I want.
I think because our planes are all intersecting at the origin, no matter what you set your gradients to, there's still going to be the same number of regions.
If the data is going around the origin.
Sorry, yes, if the data is going around the origin.
Well, but not in higher dimensions, maybe.
Yeah.
If you look at, if you change from m equal to 3 to 4 or 5,
Yeah.
you will have some sections that are not crossing over the origin.
Yeah. I mean, that's definitely the case. That's also the case if we don't weight it either, right? You have certain forbidden ordinal sequences, meaning that if you have a time delay embedding of, say, like 6, there are hypothetically 6 factorial possible symbols you can have, but not all of those get taken up.
Yes,
So
but I'm complaining about the geometry of the piece of the attractor that I'm looking at.
yes.
I can change it in that way because by comparing these two figures, it's just in terms of the section that I'm choosing from the Lorentz to look at.
Yeah, it will move the sections about, make them bigger and smaller in terms of number of points. I think in general, although Thomas disagrees, I think in general you could change the number of valid symbols with this, but to be honest, we don't know where we're going with this. This was the last. I hadn't seen anything past the definition of the weighting thing. That was the last time we talked about this on Tuesday.
Tuesday? Yeah.
I said we could do this instead, and then he went and did all of this. So I'm not sure whether that's a good thing or a bad thing. That we change the number of forbidden patterns.
I would anyway recommend that you put that one step beforehand in your talk, because illustrated.
Yeah.
Work does seem to have something like it's going nowhere currently. You don't have a nice bang
Yeah.
conclusion.
Okay, right.
You want
I
to
think
end
he-
your
I think
talk
he
on
put-
a high.
He put this here to show that he done something since Tuesday.
Yeah. No, no, so I would still rearrange it in your.
Yeah, okay.
So for the AMSI talk, how much time do you have?
Oh, like 15 minutes. So.
Yeah, so just forget it.
Yeah.
Eugene, you have a question.
Yeah, just because, for example, that's in this case, I guess doesn't it's okay. You know, you have 1 1 for the default case, and your A1 A2 is 2 and 0.05.
Yeah.
But if you go to
And then the
plot,
next-
or the plot later, there's
Yeah.
a mark. Like so these values don't normalize the magnitude of your readings, right? So if I picked really low A1 and A2, or really big A1 and really low A2, you're essentially artificially removing one observation from one dimension from your
Yeah.
output, right? So
Yeah.
if you take A1 as 1 and A2 is 0.25. Then
Yes.
one coordinate will dominate the second one, but the third coordinate has a weighting of 1. Basically,
Oh, I think not.
I don't know the I don't know.
Yeah.
But basically, the A1 and A2, like, has that been a thing that you observe where, because you're not normalizing the magnitude of the whole vector,
Yeah.
so if you pick like really disparate values A1 and A2, you're essentially like destroying or removing one component entirely.
Well, except that
You would be setting it closer to 0, right? So if you set A1 to 0, A2 to some really large value, you're essentially guaranteeing that A1's going to be smaller.
Well,
Then-
but more so because of
Yeah.
But in the more intermediate cases where these transitions are more fine, like let's say you take 1 and 0.5 or 1 and 0.75, but then the original observation, the original ordering is like the inverse of that.
Yes.
Would that be a case where the A1, A2 kind of cancels out what the original symbol was and messes that up? Like, do you need to do some kind of normalization of A1 and A2 in the ordinal? I don't know whether my question.
So you're sort of getting a point where you've got like within your vector, you would say have 2 points which are exactly the same value, so you can't order them.
It's more like a case where in the original ordinal you have a certain symbol, but A1 and A2 is like the opposite ordering of that. So it causes the two symbols to basically it destroys that kind of correlation. I'm just thinking, like,
Or you could certainly change what the ordinal sequence ends up being by applying the coefficients, right? Are you saying that something that used to be 1, 2, 3 could turn into 2, 1, 3?
I'll figure out how to ask
Yeah.
the question. But
This is also something that I haven't looked into
yeah,
in a lot
yeah.
of depth. I kind of produced this graph and went,
Yeah,
oh, look,
because-
it's interesting. There's a
because
white
your
spot there. So
your third coordinate is just the time series raw scalar value.
yes,
Your first and second are scaled by A1 and A2,
yes,
which means that means the scale of the vector is dominated by just the first two coordinates, irrespective of what the third one is. So depending on how you choose A1, A2, you could be or could not be totally disregarding that. Yeah, I forgot. Wait.
so he's saying that if, say, like A1 and A2 are much larger than 1,
Yeah, or for
You're-
example, that's
well,
one.
if you make one of them 0, then it's close to 0. But, yeah, aside from that, I'm sure. My question would be, why do you think the white line there is vaguely quadratic relationship between A1 and A2?
yes, that's interesting. I've got
I've got no idea.
no idea.
While we're on this figure, what is happening with that top row?
Yeah, sorry, I kind of hoped,
Last figure as well.
I was hoping no one would ask. I think that's just me writing dodgy code. I think that's something weird happening at the end there.
I
I,
it on the projector screen. That's
if you zoom out, then that weird bit's always on the top and left edge. So I assume there's something wrong with the code. I just zoomed in on, I did look at, say, like -2 to 2 for both A1, A2, but just zoomed in on the interesting part.
It's also
Yeah.
interesting that on that right in the middle of the quadratic, there's a bright spot, right? Which I'm guessing that's where 1 point.
Yeah,
is.
yeah.
And that is roughly the performance of that is quite similar to removing like at A2 equals 0 and just taking A1 is like 0.75 or something like that. So.
So yeah, again, I think it's similar things. Oh, actually, I'm not sure if that's happening on the left. Yeah.
So like the bright spot right in the center.
Yeah. So when we set
It's the same
A2.
performance as a case where you just remove one.
So if we're just considering,
Just
say, the
considering
first point and
lag.
the first point and the third point, right?
Yeah.
Yeah.
Which is why I'm thinking there's some normalization thing, like, because technically should that be performing equally?
I'm actually not 100% sure. I think it'll be interesting to have a look at what the actual partition looks like
Yeah.
if you select those parameter values. Yeah.
That was just more curiosity. So
Yeah. I'm not too sure.
Okay, if there are no other questions, I have, of course, my last question.
Yeah.
All the things that you're looking at are these time delay embeddings,
Mm.
events, other attractors. What is the value of your research if the embedding is actually not properly done? Because, I mean, we are doing a three-dimensional embedding of a three-dimensional object.
Yes.
That is not correct. You cannot guarantee that this is a true representation of your attractor.
Yeah.
So why did your supervisor not tell you to use a seven-dimensional embedding? And what is the value of that research if that embedding actually is not true?
Might be a question for Michael.
I've got another meeting to attend.
Not a question.
Michael.
Not a question, but a request. Could you reference the slide back up?
Yeah.
I just didn't have time to read it before. Thank you.
Okay,
Great.
thank you very much, Jason.
Thank you.
Next week is going to be Ken talking about whatever he does. You haven't sent me an abstract yet, so I can't tell you before.
It's an interesting topic, though. Whatever we're talking about.
Can I switch this off now?
Yeah,
Yeah.
unless you're keeping workshops. Yeah, there's a few.
Yeah, no, please, please.
Just
Yeah,
the
yeah,
type
yeah.
was part of the description area of the ordinal.
Yes.
4 points. I think it's. I think that should be 4. Because you've got 4, 2, 3, 1, 2, 3, 1.
Okay,
Hello?
I'm going to start. Just making it.
Hello?
Yeah. Should I slowly
Yeah, maybe.
document?
Some
Well, how about you just go from the start?
Oh, yeah. Well, actually, the surrogate,
Yes.
that's not a typo, but usually it's without replacement.
Oh, yeah. So.
Rather than, and so that's so much different. But it's all usually.
Yeah.
It's usually without, but it can be with.
Yeah. So Michael sent me a reference that you mentioned, and so the
it's
idea.
algorithm 0 is actually.
Yeah.
So
Yeah.
it's without replacement. But I think there is a variation.
I think there's a variation where you do it with replacement. I think the reasoning there is that you're not interested in reconstructing the actual orbit. You just want to mimic the
Yeah,
distribution of points in the
yeah,
orbit,
exactly,
right?
yeah. So I.
Yeah.
Yeah. Well, if we go, I think there were.
Shall I go from the start and Joe, you make it? Okay.
Are you going to do honors on the same subject?
I'm not 100% sure yet. I need to actually think about it. I actually wouldn't mind sitting down with you guys and having a chat about honors thesis.
Because one of the things that I would recommend is there is a paper by Hooke and Broomhead. I'll send you the references.
Yeah.
Very scary kind of crazy stuff. Yeah.
What was it looking at?
When basically the idea is that you can you go backwards, I think.
Yes. To
Further. This.
this thing.
So basically what they are looking at is the question of having a partition, a single partition in the flow, the size of this partition, and recording when you go through that partition. They basically only know I went through the partition, and they record the time between consecutive, so the return time
Okay,
to
right.
that partition.
And this is like
They
a very, very small partition.
Exactly, it's a very
okay.
small
Yep.
partition. And the idea there is that if you have a good enough partition, so
Yeah.
almost everywhere, and you just get the times, and you get a number which is around 7, because you need 7 dimensions for the rest, yeah. You have a one-to-one embedding of the system in these delay times. And then you can do forecasting with that shit as well. So I came across by doing some research together with
Yeah.
Yoshito,
Yeah, yeah.
who you referenced. And the idea, so when we were doing the practical research, we looked at different partition sizes. The issue was really more like getting the partition small enough and the time series fine enough so that I can actually detect the cross.
Right.
And we could see some that our method started to decay in terms of forecast skill if we didn't do it fine enough and small enough.
Yes.
So basically this is something like a question that could be taken into this question of, okay, what is a good embedding as well, or
Yeah.
a good kind of encoding. Yeah?
Yeah, okay.
I found that quite interesting.
So could you explain that process again? So you